breakthrough at the time because it reduced the 80 pages to 8 pages. Okay, so that was a factor of 10, massive breakthrough. And then the real breakthrough happened, which is that they reduced it to a single term. So when two of the gluons have positive helicity and the negative helicity, and the remainder have positive helicity, so the gluons have spin 1, so they have helicity, +1 or -1. They found the following stunning one-term expression. These 80 pages collapse to one term. I'll tell you what these symbols mean in a second. So these amplitudes were, they also showed that if all the gluons had plus helicity, or all but one had plus helicity, the amplitude vanished. So the first non-trivial one was when two of them had negative and the rest were positive. This was quickly generalized. If any two of them were negative and the rest positive, it's this amazing one-line expression, one-term expression. So this should start making you think there's something wrong with the usual way of doing things. At the time, people didn't really extract this lesson. People were thrilled that they could compute these amplitudes more easily, but they didn't think that it was a hint of a radical rethinking of space-time and quantum mechanics. Partially, well, we now know this is the tip of a massive iceberg, and that iceberg is what I'm going to tell you about in the rest of the talk. But at the time, people thought it was just accidental. One of the reasons they thought it was accidental is that when you went to even the next more complicated ones with 3 plus and 3 minus, it didn't simplify remotely as much. Okay? And in fact, even using all of this fancy technology, not Feynman diagrams, that's hopeless, but using all the fancy technology that was developed, as of 2004, the state of the art was that the 7-particle amplitude was known in papers and was written down, it occupied maybe 10 pages. The 8-particle amplitude sat on a supercomputer at CERN somewhere, and that was it. Okay. All right, but as we'll see in the rest of the talk, it is the tip of a big iceberg. But let's go back and just ask the qualitative question. Why is it that Feynman diagrams are so complicated? Is it some technical thing? Is it some minutiae of why? The answer is it isn't any kind of minutiae at all. It's something very fundamental and deep about their purpose in life. Feynman diagrams have the purpose, or the usual, when I say Feynman diagrams, I really mean the usual formulation of quantum field theory. Their purpose in life is to make unitarity and locality completely manifest. And it's precisely the desire to make unitarity and locality completely manifest that totally obscures the simplicity of the answer. In fact, this problem becomes particularly sharp when we start talking about particles that have spin 1 and higher. Let's talk about massless particles like the photon and in some approximation the gluon. And this is the crucial point. The photon, for example, has 2 helicities, +1 or -1, right? To spin 1 particle, if it was massive, you could boost to a frame where it was at rest and rotate the spin around to see that it has 3 degrees of freedom. But if it's massless, you can't boost to a frame where it's at rest. And all you can say is that it has angular momentum 1 or -1 along its direction of motion. So all it has is helicity. Now, so let's say we want to describe the interaction of a photon or a gluon in a way that makes locality in space-time manifest. The way that we do that is to group these particles together into fields, and then write down local interactions for these fields. So we do that. We write down what you might recognize as a vector potential field. Everything is Lorentz invariant, so this is a 4-vector. Mu is an index 0, 1, 2, 3. And here's a plane wave solution, which you can think of as a polarization vector times e to the IPx. But you see we have a problem. There's 4 components here, this epsilon, 0, 1, 2, 3, but the polarization has 2 helicities. There's too many degrees of freedom in that polarization vector. Now we can impose some constraints on this guy. We can say that this polarization vector is orthogonal to the momentum, for example. But that still only knocks us down to 3 degrees of freedom, not 2. We've got to get down to 2 degrees of freedom. And then we're stuck. There's simply no way we can get down to 2 degrees of freedom. The only way to do it is to introduce a totally new idea. We're forced to say that the only way we can proceed is to say that 2 polarization vectors that differ by something proportional to the 4 momentum actually describe exactly the same physical state. So this is the idea of a redundancy. we say that there isn't a one-to-one correspondence between a given polarization vector and a given physical state, but a whole family of polarization vectors that differ by something proportional to the momentum correspond to the same physical states. This is the redundancy that in position space, some of you may recognize as a gauge, what's often referred to as a gauge symmetry in older books. But there's no such thing as gauge symmetry. Often older books will rhapsodize about the beauty of symmetry. The symmetry determines everything. And gauge symmetries are especially beautiful and important. And this is as wrong as could possibly be. There's no such thing as gauge symmetry. Gauge symmetry is a complete fraud. It's a complete fake. It's a figment of the human imagination. It has nothing whatsoever to do with actual physics. The actual physics, you have a bunch of massless particles interacting with each other in some way. Human beings, you and I, in order to describe this physics in a way that makes locality manifest and unitarity manifest, find it amazingly convenient and useful to introduce this redundancy into our description of the physics. I'm not saying it's not useful, it's massively useful. But it is useful the way the English language is useful to communicate with each other. And other people might find the French language useful to communicate with each other. And there's nothing better or worse about one compared to the other. It has no actual content in and of itself. And it's actually worse than that, because this is what you're forced to do to describe physics in a way that makes locality and unitarity manifest. But, as you see, it forces you to drag around all of this unphysical stuff around with you as you're doing the calculation. It's exactly this unphysical stuff that makes the answer 80 pages of work. And which all cancels out miraculously at the end when you actually compute an actual observable, as it should, because it's not there. But dragging it around is what makes things so complicated. So this is why I bothered to go through both the highfalutin and the concrete motivations, because you see they beautifully dovetail with each other. On the one hand, we strongly suspect that locality isn't fundamental. It may well be even that quantum mechanics needs to be deformed in some way. And we decided that a general strategy for pursuing these problems would be to figure out some way of reformulating standard physics in a way that didn't make locality and unitarity manifest. On the other hand, totally ignoring those highfalutin arguments, we have our standard formulation of physics screaming out, please do something different with me, because making locality and unitarity manifest is totally obscuring the actual simplicity and amazing structures of the answer. So when something highfalutin and something concrete both lead you to the same conclusion, you sort of drop everything you're doing and you start working on the problem. And as I mentioned, all of this structure has been sitting under our noses for 60 years. Many of the things that I'm talking you could have been discovered in 1955, 1965, 1975, any time. Okay? But you had to know where to look. And they weren't discovered back then, but they were discovered 3 years ago, 2 years ago, 4 years ago, and so on. And as I mentioned right at the start, remarkably, it seems to combine ideas from string theory, twistor theory, integrable systems. Most bizarrely and excitingly to some of us, it clearly involves some very deep and beautiful ideas in algebraic geometry that have never ever had anything to do with physics in the past, but not only seem to have something to do with physics, but seem to be sitting at the very heart of a second way of thinking about this picture of scattering, where there isn't any space-time. Scattering without space-time, where locality and unitarity emerge from some second formulation. And we'll see some hints of what that second formulation looks like, and the sense in which this emergence occurs. Okay, can you tell me what time it is?
It's about 3:15.
Okay, great. So let's quickly go through some of the cast of characters. So I'm going to talk about I'm talking about the scattering of gluons, for this purpose, just so I go well, let me just say, good old-fashioned gluons inside the proton have color. Quarks have a color, red, white, and blue. Gluons have colors and anti-colors. So we can represent that diagrammatically as drawn in the lines of an arrow one way and an arrow the other way. And so if we wanted to sum up Feynman diagrams, we would draw pictures that look like this. Things that look like trees, and then things that have loops in them, little internal loops corresponding to virtual particles that you can make and annihilate. If you have to sort of integrate over all the possible momenta those virtual particles can have, So these loops are the place where the more intrinsically quantum mechanical effects come in. But anyway, the whole thing is in quantum amplitude. And there's various nice limits that people have known about for a long time, which simplify thinking about things. There's a limit where we mentally imagine the number of colors is very large, and in that limit, it turns out that the only diagrams we need to consider are the ones that can be drawn on a plane, so-called planar diagrams. And also that we can nicely talk in this limit about the thing that we have to integrate. Even before doing the integral to get the final answer, there's a nice notion of the integrand for these loops, which depend on some unknown momenta of virtual particles that we have to integrate over. We think about all the momenta as incoming, so that momentum conservation is just the statement of the sum of all the momenta added to zero. So at the moment we're talking about an object that depends on momentum, velocities, and these loop momentum variables. Now, there's a couple of things that, especially some of the undergraduates here, if you take nothing concrete away from this talk, you should take this little 2x2 matrix away and learn to love it, because it'll show up again and again in your life. So I want to talk a little bit about a nicer way of thinking about the kinematics of the external particles. So we're talking about massless particles. Normally, the way we think about this is we have a 4-vector whose energy component is equal in magnitude to its 3-vector component. But there's a nicer way of talking about it, which doesn't force us to use 4 variables that are constrained and related to each other. Right? There's an easier way of talking about it. Now, this is the really cool trick. It's actually not a trick, but anyway. It looks like a trick until you understand that it's not a trick. But imagine taking this 4-vector, and now I'm going to make, associated with this 4-vector, a 2x2 matrix. The way I'm going to do it is I'll take the 0 component and I'll multiply it by the identity. So there it is, P0, P0. But I'll take the spatial components and I'll dot them into the Pauli spin matrix.